Hello, my dear students. Welcome to uh, one more classes on econometrics. So, in last videos, we were discussing about the problem of multicollinearity and its consequences, detection method, and how we can remedy the problem of multicollinearity. Similarly, today, what I am going to discuss with you is the another problems called heteroscedasticity. When we discuss about the heteroscedasticity, or when we discuss about the assumptions of classical linear regression model, we assume that the disturbance term or the error terms, okay, is homoscedastics, or the variance of the error terms is constant for all, or variance of error terms conditional upon explanatory variable is same for all observations. Okay, so in such cases, as I told you, homo means what? Homoscedasticity is basically a Greek word, origin from two Greek words, homo and scedasticity. Homo means equal and scedasticity means variance or spread. Okay, so homoscedasticity means equal variance. So equal variance of what? It is not equal variance about the dependent variables. It is not about equal variance of the parameter or equal variance of this explanatory variable, but equal variance of the error. Okay, so the error terms or errors from the regression model should be equally spread, or the spread of the error term should be equally spaced. That's called homoscedasticity. Okay, so when we come to the example that we have discussed, when we discussed about the concept of regressions, we were taken the consumption and income examples, consumption of 60 families. Okay, so in that time we were divided the 60 family to different income groups. Okay, income groups 80, 100, 120, 140, something like that. Okay, so if you look at the graph, what you can observe here, you can observe that this is here, it is y is given, or the density function of y. Okay, and in the x-axis the income is given. Okay, so in the y-axis it is the density functions. Okay, and this is called the consumption lines, consumption functions, and this line is called what is the average consumption line. Okay, but if you look at different income groups, this x1 is one income group, x2 is another income group, x3 is another income group, x4 is another income group. Okay, so what is this line, what is this curve is showing? This curve shows the error terms of those people who are having the income level x1s, and this is the error curves or error curve of the error terms of those whose income is x2, and this is x3 income groups, and this is x4 income groups. Okay, and if you look at the spread of these curves, you can see that all the spreads are same. Okay, the spread of x1, x2, x3 and x4 are same. Okay, so this is the situation of equal spread. Okay, so these curves are error curves. Okay, and these error curves are the spread of this error curves are looking the same. That means here the variance are equally distributed, or the variance of these error terms are equal. Okay, but in real situations, or in reality, when we deal with real economic data, these assumptions of homoscedasticity may not always hold. There are certain cases where the variance are heteroscedastic. That means hetero means unequal, scedasticity means spread. So the heteroscedasticity means unequal spread. That means the variance of the error terms are not of the same. In different income group, they are having different spreads. Okay, so if you look at the graph, you can see this x1. X1 is the who is the x1? X1 is the lowest income groups, and x2 their income is better than that of this or higher than that of the x1, and this x3 they are having the highest incomes. Okay, so when we take the different income groups, there are certain people they may be poor, sometimes they may be middle income class, and sometimes they are some people they are very rich. Okay, so if you are taking the data from your locality, there will be different individual whose income will be different. And if you draw a error curve for these poor peoples, okay, you are getting one shape, and if you do it for the middle income group, you are getting the other shapes. Okay, and if you take the rich group, their variance are very different, very high. Okay, so usually the variance are measured by the distance or the spread of the curves, and the mean is measured by the height of the curves. Okay, so here you can see that the height are different. Similarly, the variance is also different, or the spread is also different. What does it mean? Poor people, middle income people, and rich people, all of their error terms condition upon their consumptions or condition upon their income are different. Okay, so there is a heteroscedasticity here. Okay, that means if you're like in your locality there are different income groups, all of them will behave differently. Different income groups will behave differently. Okay, so there's a problem of heteroscedasticity. Okay, so suppose assume that this is your equation y is equal to beta 1 plus beta 2 plus beta 2 xi plus u. Okay, in homoscedasticity what we assumed, variance of ui is equal to a constant number. Okay, then it can also express in terms of expectation. Expected value of ui square is equal to small sigma square. This is the case of homoscedasticity. Okay, then what is heteroscedasticity? Here variance of ui is small sigma I square, but here you cannot see the I. So what this I shows? I's are basically different cross sections. That means first individual I1, second individual I2. Okay, so variance of ui is not constant. So smart sigma I square means what? If I is equal to 1, then he may have one variance, and if I is equal to, the other fellow is having the other variance. Okay, so similarly we can also express this term in terms of expectations. Expected value of ui square is equal to variance I square. That means if individual, the variance will change when your I changes. What's I? I is your cross section unit. Okay, yes. Then why we are having the heteroscedasticity in our data, or why we are if you look at most of the primary data, especially the cross-section data, there will be a problem of heteroscedasticity. Okay, so what is the reason for this heteroscedasticity? There are many reasons. Okay, the first reason is scope of choice. What does the scope of choice means? For example, if you have sampled 50 individuals, okay, then when the variance will be the same, if all of the 50 individuals is having the same consumption pattern, okay, and when they will have a same consumption pattern when their income is same. Okay, when all of this 50 people's incomes are same, they may have almost similar, not exactly, almost similar consumption pattern. Okay, But if you look at the reality, in your location, all of the people are having the same individual, same income, same consumption pattern. It is not possible. Okay, some may be poor people, some may be the richest peoples. Okay, some may be the middle income groups. Okay, so here 50 are richest, 50 are in the middle income groups, and 50 are very poor peoples. Okay, so here if we want to predict the consumption behavior with wealth, automatically the wealthier individuals might have greater variance in their consumption behavior. Similarly, the poorest people, they might have less variations in their consumption behavior. Okay, yes. So the next one is learnings by doing, or learning. What is meant by learning means what? In certain examples, if individual is having the highest learning capacities or highest experience, they may have the variations. If you look at the wage example with experience, it shows that it is likely that the variance is reduced among those with more experiences. Okay, those who are having more experience, okay, their variance will be very low. Those who have less experience, their variance will be very high. Okay, so those who are having high experience, okay, their variance will be reduced. Okay, then the third one is the first one is the most important problem when we are dealing with cross-section data, and the second, learning by doing, or learning is basically confined to certain examples, example like wages and experience. Okay, and the most important reasons for heteroscedasticity is the use of cross-section data. Okay, so what is meant by cross-section data? The data collected at the data collected from different the data collected for different individual or different sessions at the same unit of same time, that the unit of the time is same, or the data collected at a point of time for different cross sections. For example, suppose you are learning about the research and development expenditure in a particular firm in a particular district. If you are saying that in Calicut district, what is the R&D expenditure? Okay, in Calicut district, as you know that the firms are different. You will find the firm with high size, small size, medium size. Okay, so in all these different firms, this R&D expenditure will be the different. Okay, and their intensity as well as the variability will also differ. Okay, especially the high firms, the large firm will spend more on R&D, but small firm will not spend that much amount for research and development. That means each and different firms will behave differently. Okay, so if you are taking the cross-section data, different individuals involved or included in our observation will behave differently. That's why in cross-section data we can expect heteroscedasticity problem 99%. Okay. Similarly, the next reason is the presence of outlier. What is outlier? Outlier is nothing but either very small or very large value in a data set compared to other values in the data set. Suppose the data is 1, 2, 3, 4, 5, something like that. Okay, then there is one value which is 100. Then 100 is the value is outlier when you are comparing with all other values. Okay, yes. Similarly, when you take the yes, this is the case of the presence of outliers. Okay, so if you have a very small value or very large value compared to other values in your data set, okay, then there will be an outlier, and this outlier will have produce heteroscedasticity problem. Okay, Then the next reason is the specification errors. What is meant by specification error? It is nothing but omitted variable bias, incorrect data transformations, incorrect functional forms. Okay, so omitted variable bias means certain important variable in our model are excluding. Okay, or certain irrelevant variables are we are including. Both are called omitted variable bias or inclusion variable bias. Similarly, if we are wrongly transform our data into ratio scale or first difference scales, okay. Similarly, as we have learned many different kinds of functional forms and linear, non-linears, okay. So in a particular situation, we have to adopt the best suitable functional forms, okay, theoretically. But if we have wrongly uh, select this data, we have wrongly selected uh, this kind of specification or wrongly selected the functional forms. So in all these three cases, we can expect certain kind of heteroscedastic problem in our result. Okay, and the last reason is skewness in the distribution. In most of the economic variable, especially if you take the case of income, wealth, education, there will be a problem of skewness. Okay, then if there's a problem of skewness, then surely we can expect a problem of heteroscedasticity in our data. Okay, then if there is a problems of heteroscedasticity, then how it will affect our regression results or regression models. Okay, in the case of heteroscedasticity, the estimator is still linear and unbiased. If you look at the properties of OLS, in the case of heteroscedasticity also, the model will be linear and the results will be unbiased, because in order to establish the linearity as well as unbiasedness properties, we don't need to have the error we don't need to homoscedastic error. Okay, because these homoscedastic errors are nothing to do with unbiasedness property as well as linear properties. Okay, similarly, estimators will remain consistent as n increases, estimated beta values will converge to true beta values. Because in order to prove the consistency property also, we don't need the homoscedastic error. And betas are asymptotically normal distributed. That means if you use large sample size, your betas will be asymptotically normally distributed. Okay, but the major problem is in your results it may not be in the coefficients may not be best or efficient. Okay, in the case of heteroscedasticity, betas does not have the minimum variance in the class of all unbiased estimators. Okay, so the major problem with heteroscedasticity is it will violate or it will affect the best property as well as efficient properties. Okay, so in the case of heteroscedasticity, the estimators are not best and not efficient. That's why it is not best linear unbiased estimator, only linear unbiased estimator. In the blue, the B will not be happened. Without B, the blue will become LU, LU. Okay, yes. Then I have provided one video. Okay, in that video, uh, we have seen that this property, that means the problem with this the consequences of this heteroscedasticity is proven. Okay, so let me check it once again. We have an equation like yi is equal to beta 0 beta 1 xi plus ui. Okay, then what is this variance of beta 1? It is nothing but expected beta 1 minus expected beta 1 whole square, because variance of u is what? Expected ui square. Okay, so similarly, we can find that variance of beta 1 is expected beta 1 minus expected beta 1 square. Okay, because here we assume that beta 1 is nothing but beta 1 minus the beta 1 cap minus expected beta 1. Okay, then here we have already found that the expected beta cap 1 is equal to beta 1 from where? From unvariance properties. Okay, now our equation is variance of beta cap 1 is equal to expected beta cap 1 minus beta 1 square. Okay, this beta 1 has appeared here. Okay, and we have already learned that beta cap 1 can be expressed as sigma ki into yi. Okay, this is from linearity properties. Sigma ki is equal to yi. Okay, y can be expressed in terms of k, and beta cap 1 is equal to sigma ki into yi. What is the sigma ki into yi? If you substitute the value of yi is nothing but an equation. What is that equation? Beta 0 plus beta 1 x plus ui. Okay, then if you substitute this value in this equation, it will be beta 1 cap is equal to beta 0 sigma ki plus beta 1 sigma ki xi plus sigma ki into ui. And you know that sigma k is equal to 0, so this will be 0. Sigma ki into xi will become 1. Okay, this is beta 1, and remaining term will be sigma ki into ui. Okay, so from the properties of k, we have already found that sigma k will be equal to 0 and sigma ki xi will be equal to 1. So see, first term will become 0, second term will become beta 1 alone, and third term will become sigma ki into ui. Okay, now expected beta 1 is equal to beta 1 plus sigma ki into expected ui. Now we are taking the expectation symbol. So beta cap 1, take the expectation. So it will be expected beta cap 1 is equal to expected beta 1. It will be expected beta 1. Beta 1 is a constant. So the expectation of constant will be the same constant. So beta 1 plus sigma ki into, you take the expectation of ui. Expectation of ui. And as you know that this expectation of ui is equal to 0 by the assumption 3, then what remained there? There remain beta 1 plus sigma k. We have already seen that sigma k is also 0. What will happen? Expected beta 1 is equal to beta 1. Okay, so we have proven that still if there is a problem of heteroscedasticity, the unbiasedness property will remain unchanged. Okay, now this expected beta 1 cap minus beta 1 will be equal to sigma ki ui. If you take expectation of beta cap 1 minus beta 1, it will be equal to sigma ki into ui. Okay, now what we are doing? We are expanding this sigma ki into ui. We have seen that sigma beta cap 1 minus beta 1 is equal to sigma ki into ui. Then what is the variance of beta 1? Variance of beta cap 1 is nothing but expected beta cap 1 minus beta 1 square. Okay, so what I am doing is I am taking this beta cap 1 minus beta 1 square, okay, like this. So beta cap 1 minus beta 1 is nothing but sigma ki into ui. Then beta cap 1 minus beta 1 square will be what? Sigma ki square ui square. You got the point? Yes. So beta cap 1 minus beta 1 is sigma ki ui, but here beta 1 cap minus beta 1 square. So it will be sigma ki square into ui square. Now, what is this sigma ki square into ui square? It is nothing but sigma ki square ui square plus 2 into sigma ki square. Okay, so this is just nothing but the cross product. Okay, so it means that if we are having only three values, 3k and 3u, it will be sigma k1 square u1 square plus k2 square u2 square plus k3 square plus u3 square. Then we take the cross product, 2k1 k2 u1 u2, 2k1 k3 u1 u3, 2k2 k3 ut u3. That means if we have three variable k1 k2 u1 u2, okay, k1 then k2 k3 k1 k3 u1 u3, then k2 k3 u2 u3. That means three pairs are possible when you are having three observation, 1 2 3, 1 1, sorry, 1 2, 1 3, 2 3. Similarly here also we can find out the cross product of this ki and the ui. This is the case of three variable, three observations. Okay, so here using the properties of no autocorrelations, we found that ki, k2, u1, u2, okay, expectation of k1, k2, u1, u2 will become 0. Okay, so what will happen? Now only k1 square remains in u1 square. This terms, okay, this terms goes, and this terms also goes. The remaining term will be k1 square u1 square plus k2 u2 square plus k3 square u3 square. Okay, then you take the expectations. It will be k1 square expected u1 square plus k2 square expected u2 square plus k3 square plus expected u3 square plus, here we are taking only two variable. Okay, if you are having many variables, then it will goes like that. Okay, so variance of beta cap 1 will be sigma expected ui square is nothing but the variance. Okay, so k1 square variance 1 square, k2 square variance 2 square, then k3 square variance 3 square plus, if you have a many observation, this will goes. Okay, so what happened? Variance of beta 1 is equal to sigma k I square variance I square. Okay, this will be sigma k is what? K is nothing but sigma xi divided by sigma xi square. Okay, so this term will be sigma xi sigma xi divided by sigma xi square whole square, and it will be variance is equal to sigma xi square then small sigma I square divided by sigma xi square whole square. Okay, it means that whenever your I changes, what happened? This variance will also changes. Okay, so for different cross sections you may have different variants. So this is the major problem with this heteroscedastic variant. Your third property, that means the variance will not be minimum. Okay, so if the variance is not minimum, the confidence interval based on the variance will be unnecessarily large. So what happened? Standard error will be biased. F test, T test we cannot use. If we use, it will provide inaccurate results. Okay, so if we use Euler's and usual variance formula despite of heteroscedastic problems, whatever the conclusion we derive from the Euler's will be misleading, and the prediction based on the Euler's result may go wrong. Okay, so this is the major consequences with this heteroscedasty. Okay, so in the next video I'll provide you how we can detect the presence of heteroscedasticity. Okay, so thank you.